Today, I'd like to do an explicit calculation of uncertainties in quantum mechanics. Specifically, I'm going to be considering a spin-1 particle and looking at the spin uncertainty relation that we've studied before. That relation tells us the uncertainty in a measurement of Jx times the uncertainty in a measurement of Jy is greater than or equal to h bar over 2 times the absolute value of the expectation value of Jz. This came from the commutation relations for angular momentum and the usual uncertainty relations. We're not going to derive that here. We're just testing it out. Today's plan is to test it out. In particular, I want to verify that this relationship holds true in the case of the specific state psi. I'm writing this ket psi as a linear combination of the three spin-1 spin basis states in the z basis, the sz basis. So 1/3 times the 1,1 state plus 2/3 times 1,0 plus 2i over 3 times 1 minus 1. You can check that that state's normalized. It comes out to, the amplitude sums to 1 if you sum up all these things. Psi bra with psi ket will give you 1. And our goal is to work out both sides of this equation and figure out what's going on. So, okay, just to remind you, we're going to do this in matrix language. We could use bras and kets the whole time, but it's going to be much easier, much more straightforward to use matrix language. And to do that, we're going to notice that the usual representation, the SC basis, 1, 1 is our first element, 1, 0 is the second, 1 minus 1 is the third element of a three-dimensional vector. It's a three-dimensional vector space of states. So to do this calculation, we're going to have to calculate several things. Obviously, we'll have to calculate the expectation value of Jz for this state. But we're also going to need to calculate the expectation, or the uncertainty in Jx measurements and the uncertainty in Jy. To do that, I'll remind you of what we know. The equation we can use to find the uncertainty in a measurement is equal to the square root of if we're doing a measurement of the operator A, that uncertainty is equal to the expectation value of A squared minus the expectation value of A quantity squared, and then the square root of the whole thing. That's our equation for delta A. And so we're going to apply that for A equals Jx and A equals Jy for those two operators. So in other words, we need to calculate the expectation value of Jx and Jy and Jz, and also the expectation value of Jx squared and Jy squared. It's a bit of a calculation. It'll be a bit of a slog, but we're going to go through it. It'll give us some practice with matrix quantum mechanics and spin-1 basis, and it will also give us a way to check this uncertainty relation and see how it comes together. Obviously, the relation should hold for any state I write down, not just this particular one, but we test them one at a time. So here's the plan. Let me remind you, pulled out of our textbook or calculated in all sorts of whatever way you want to, all sorts of different ways, let me remind you of the matrix representations of the angular momentum components, Jx, Jy, and Jz. The x operator gets this matrix with a bunch of 1s and 0s in it, with an h bar over square root of 2 out front. The Jy operator gets a bunch of i's and minus i's, with the h bar over square root of 2 out front. And Jz, in the z basis, obviously is simple. It's in its own basis after all. H bar 0 minus h bar is that matrix. It's the simple basis comes out nicely. So those are our matrices. Those are the matrix representation of these operators. And I guess probably a place to start is to work out the matrix representation of our state psi in the same basis. And we can say that psi is represented by 1/3, 2/3, and 2i over 3. There's our vector. State size coming out nicely that way. And then we just need to go about solving this thing, finding all these expectation values, and then calculating all the uncertainties we need. So let's just make a table of those expectation values as we go about this and see what it comes up with. First, maybe we can do the Jz expectation value first, because it's really easy. Remember, the expectation value for Jz in this state, let's go ahead and erase this. The expectation value for Jz in this state, we can find, since we're already written in terms of the eigenstates of Jz, we could say that the expectation value for Jz is equal to the probability of the +1 state, 1/3. That's an absolute square. That's the probability of the +1 state times plus h bar is Jz plus 1, plus the absolute value of 2/3 times 0 plus the absolute value of 2I over 3 times minus h bar. If you do that, that gives us h bar over 9 plus 0 minus 4/9 h bar, or in other words, minus 1/3 h bar is my expectation value for JZ. So that one's done and it's quick and easy because we know probabilities for each of the three things just by reading them off of our coefficients in this basis. The other thing we could have done, and the thing we're going to do for the other two, JX and JY, to find those expectation values, is use matrix language. We'd like to use this in matrix language. We'd like to say that the expectation value of JY, or yeah, we'll do X first. Expectation value of JX is equal to psi times the JX operator times psi, the bra, the operator, the ket, sandwiched together. That's the expectation values for you. And in our basis, the psi bra is just the conjugate transpose of this psi. So I'm going to factor out the 1/3. I'm going to write this as 1/3 times 1, 2, 2i, just so I don't have to deal with quadrivial fractions. If I do that, my complex conjugate is 1/3 times 1, 2, minus 2i. Then I put in the representation of JX in this basis. We saw that was h bar over square root of 2 times 0, 1, 0, 1, 0, 1, 0, 1, 0 times 1/3, 1, 2, plus 2i. There we go. This is the matrix calculation I can do to calculate the expectation value of JX, just putting in that JX there. So factoring a bunch of, well, I won't factor out yet. I'll do this calculation. That's 1/3, 1, 2, minus 2i times these two things together. I'll get h bar over 3 square root of 2 times, doing this matrix multiplication, I get 2, 1 plus 2i, 2. And now I have a matrix multiplication I can do again. Just this thing gives me h bar over 9 square root of 2 times, what do I get? 2 plus 4i, multiply those, plus minus 4i. As we hope, since this is the expectation value of a Hermitian operator, the imaginary parts cancel out. We end up getting, the 4i cancels with the minus 4i, we end up getting 4 in there, we get 4 h bar over 9 square root of 2. Or if we want to rationalize the denominator, which is sometimes nice, we could write this as 4 square root of 2 over 18. Hey, I could simplify that, couldn't I? Yes. 2 square root of 2 over 9, all times h bar, of course, times h bar. 2 square root of 2 over 9 times h bar is my JX expectation value. And if you work it out, if you do put that into a calculator, that'll give you roughly, what did I get for this? 0.314, 0.314, that looks too tempting, 3143 h bar. No hidden pies floating around. So that's our JZ expectation value, or sorry, JX expectation value. We know JZ, JX, and next we're going to do JY. Before I do JY though, I know I'm also going to need the JX squared expectation value. Let's just finish up all the X stuff first before I erase any of this stuff, since I have a small board to work with. Let's work out what the JX squared expectation value is, since we'll need it. For JX squared, we do a very similar calculation. We know the expectation value of JX squared is going to be psi bra, and then inside JX squared, so JX operator times JX operator, and then psi ket on the other side. The thing that's neat about this, the thing that will give us a shortcut here, is that notice this guy and this guy, we know JX is Hermitian. Just as a shortcut, we know this is Hermitian. these two things that I've underlined separately are complex conjugates of each other. And in fact, I already did this calculation. Jx applied to psi in matrix language is this guy right here. This h bar over 3 square root of 2 times this particular column vector, that is the Jx psi state. So I can find this expectation value, be totally sneaky, just take a shortcut, steal my calculation from over here. In matrix language, in the SZ basis, represented in the SZ basis, I'm just going to take the conjugate transpose of this times itself. That gives me h bar over 3 square root of 2 times conjugate transpose 2, 1 minus 2i, 2, times the original thing, h bar over 3 square root of 2 times the matrix 1, or no, sorry, not 1, 2, same thing there, 2, 1 plus 2i, 2. Multiplying these together, what do I get? I get h bar squared over 9, 18, h bar squared over 18, factoring out the common front, the prefactors, times, then adding this up, 4, plus this absolute square comes up to be 1 plus 4, plus 4. In other words, 13 over 18 h bar squared is the result we get there. And I calculated out numerical value for that earlier. Did I calculate out the numerical value? I did, and then I didn't write it down. Well, you can plug that into a calculator as easily as I can, I suppose, and get a numerical value for that constant. But it came out actually pretty nicely, if you were square root, since it's a squared thing, I guess. And we get this. So I may as well go ahead and calculate what delta Jx is. It's the square root of this guy, 13/18 h bar squared, minus this expectation value squared, 2 square root of 2 over 9 h bar, quantity squared. If you work all that out, I'm not going to subject you to me going through and doing a bunch of boring algebra, but if you work all that out, the delta Jx that I get ends up being h bar over 9 times the square root of 101 over 2. Or numerically, since that's an obnoxious thing to work with, numerically, that's about 0.79 times h bar is my delta Jx that I come up with. So I already have 2 of the 3 pieces I need for my calculation, for my final uncertainty calculation. I just need to do the exact same thing now, repeat this calculation, except for the Jy state. And maybe I could be really lazy and try to reuse some of my writing on the board here, see what changes. For Jy instead of Jx, this might work. For Jy instead of Jx, I'm going to calculate a different thing. If I want to do Jy instead, well, I'm going to do this same thing. This is going to be Jy that I'll change. And so that means my matrix representation changes as well. My matrix representation, I need to make sure I get this right. I've got h bar over square root of 2 times the matrix 0 minus I 0, I 0 minus I 0, I 0 in that space. And so I can do this product. When I do the product, this term will change. I'll leave this, I'll do the second 2 first, put that together. The prefactor is going to be the same. That's good. H bar over 3 square root of 2. H bar over 3 square root of 2 times, when I do this product, I'll get minus 2i as my first component. Let's see, I plus 2, so 2 plus I, and minus 2i, it looks like. Is that right? Yeah, minus 2i, 2 plus I, yeah, 2 plus I. That should be that's my product there. I have that come together. Did I forget? No, okay. Okay, so I've got this story. I've worked that out. Make sure that's right. Yeah. No, that's a plus 2i. That's a plus 2i. I knew I had something wrong. Plus 2i for this one. So, okay, minus 2i, 2 plus I, and then plus 2i down there. Same prefactor. So hey, now I multiply this all out. This is where it becomes different. I need to change my results here. Multiply it all out. Multiply these together. I get h bar over 9 square root of 2 times, what all do I get? I get minus 2i, 1 times 2i, plus 2 plus 2i, and then minus 2 times 2, 4, plus 4, it looks like, is my, oh, did I multiplied that wrong again. 4 plus 2i. 4 plus 2i plus 4. There's my product of these two vectors, of the row matrix times column matrix. Again, thank goodness, this is a Hermitian operator. I'm taking the expectation value of a Hermitian operator. I should get a real result, and indeed, the minus 2i and the plus 2i cancel out between those two terms. I'm left with just 8 inside, so this is 8 h bar over 9 square root of 2. Or, if you want to write it this way, you can write it as 4 h bar over 9. That should work. 4 square root of 2 is what I meant. 4 square root of 2. 4 square root of 2 h bar over 9. And that's my expectation value for jy. I've gone through, done the same calculation, 4 square root of 2 over 9. And if I wanted a numerical value for that, that is 0.6285. 0.6285 times h bar is the numerical value. So there, I've gone through, I've found the jy expectation value. Let's do the same thing up here. Find jy squared. And again, it is a very parallel. Jx and jy, it's the same calculation basically. Jy squared is jy operator with jy operator. Again, jy is Hermitian, so doing this is just a conjugate transpose. These two are conjugate transposes of each other. I can take this value, same thing there, copy it over, bring this guy over, h bar over 3 square root of 2 with my minus 2i, 2 plus I, and plus 2i. Conjugate transpose of that gives me plus 2i, 2 minus I, minus 2i over here. That's just, again, copying this over because, as we saw earlier, that's this thing in brackets down here. Multiplying it all together. Same story as before. What do I get? That gives me 4. The prefactors I'll combine again in this exact same way. I get 4 plus, let's see, 4 plus 1 for the absolute square of that term, plus 4, comes out the same. Looks like it is 13 over 18 times h bar squared is my answer once again. And so for delta jy then, my delta jy, my delta jy, I copy this down again. That's the same as it was before. I copy down 4 square root of 2 over 9 instead of 2 square root of 2 over 9. I'll just change that one piece. 4 square root of 2 over 9. And again, I won't make you suffer through all my calculations here. I'll just tell you, when I do this, I get h bar over 9 times, you can tell it's going to be similar calculations since the numbers are so similar, I get 53 over 2. Weird numbers. There's nothing special that would make a calculation like this come out nicely. Numerically, this delta jy comes out to be about 0.57 h bar as my uncertainty in my measurement of jy for this particular state psi that we're considering. So okay, putting that all together, let's test out our uncertainty relation. Let's, I'm going to leave that up there just because we're about to use it and we don't need much more space. Let's test out our uncertainty relation. I've got my two things, if I'm going to write them up, I know that delta jx times delta jy, I'm not going to multiply it out in explicit form. I'm going to use the decimals because, my heavens, it's a pain, is approximately equal to, and grab that again, 0.79 h bar times 0.57 h bar. That product comes out to be essentially 0.45 h bar squared. That's my product. I'm supposed to be comparing this to the absolute value of the expectation value of Jz times h bar over 2, which came from our uncertainty relation back in the day. Well, I know the expectation value of Jz, it's 1/3 h bar. This comes out to be just h bar over 2 times absolute value, 1/3 h bar, which is 1/6 h bar squared, or 0.167 h bar squared. If I compare these two things, you can see that this is indeed greater than or equal to the other side. So our relationship does hold. We've gone through this whole calculation. We've calculated the product with the uncertainties, and it is bigger than the minimum uncertainty we would have from the uncertainty relation. That's the story. Mostly this is just a practice with matrix mechanics calculation, but it gives you a sense of how it works, how you can apply this in a particular case. Hopefully it gives you some practice. If you wanted to do this without going into matrix language, it would be more of a pain, because the Jx and Jy operators are kind of a pain to apply to Ket's psi in the z basis. You would probably end up having to apply them to the Ket in terms of J plus and J minus, the raising and lowering operators, and it becomes really quite a headache to do. Lots of messy stuff. We could do that, but why do it? Matrix mechanics, the matrix form, matrix representations of all these things work really well, and they let us do these calculations in a nice, easy way. That's our story, and hopefully that's a decent example of how you do a calculation of uncertainties in quantum mechanics.